Welcome to the second lecture of this course on principles and techniques of modern radar systems. Now, the first lecture was an introduction. We have seen various history of radar development, then we have seen the applications. Now, today we will see the technology, the simple things. First, radar bands. Actually, radars can operate in radio frequency bands. So, there was actually, as the historical development pointed out, that it was invented due to first defense applications. So, initially there was some secrecy, because it is very important to keep it secret from enemies what is the band of frequency in which the radar is operating, because if it is known to the enemy, then enemy can fool the radar. That is why there was some secret nomenclature, but after the World War in 1953, the scientific community, they actually tried to make this radar band nomenclature scientific. So, that first we will see. So, you see that actually audio frequency. Now, what is audio frequency? All electronic students know that audio frequency is, we can roughly say, we know 20 hertz to 20 kilohertz, but for radar actually you see that the velocity of light is 3 into 10 to the power 8. So, we will make instead of 2 everything in terms of 3. So, we can say audio frequency is 30 hertz to 30 kilohertz. Okay. So, this is not radio frequency. And what is video frequency? So, we know that if you want to communicate a video signal, then roughly you can say that up to 30 megahertz you can go. Now, actually the radar bands, they start just above this 30 kilohertz. So, generally radars, radars are a high power signal. So, if they are co-located with other bands, then there will be problem. Obviously, these audio frequencies when communicated, they are communicated in some other frequency. Obviously, in these bands you will see that there are lot of interference possible, because these bands were mainly communication, and initial days radars, they also were using those equipments. Later gradually they shifted to more higher frequencies, gigahertz frequencies, and defense never operated in these lower frequencies, though in World War II they operated in the communication frequencies, but gradually they, after World War II, they shifted to the real microwave frequencies. But while nomenclature coming, these radar frequencies, they got divided into this, starting from very low frequency. Now, very low frequency is anything up to 30 kilohertz. Then anything between 30 kilohertz to 300 kilohertz is called low frequency. These are bands. So, I can say that these are radar bands. Then medium frequency 300 kilohertz to 3000 kilohertz, or we can say 3 megahertz. Then high frequency is 3 megahertz to 30 megahertz. Very high frequency, V stands for very. So, 30 megahertz to 300 megahertz. Then came ultra high frequency. So, 300 megahertz to 3000 megahertz, which can be called 3 gigahertz. Then super, this S stands for super high frequency. So, this is 3 gigahertz to 30 gigahertz, and E is extremely high frequency. So, that is 30 gigahertz to 300 gigahertz. So, you see it is always a change of decade. Now, accordingly, actually these bands, they were, while giving the name actually these were the communication people's name, radar people scientifically they tried to give this name. So, this was called band 4. So, first VLF band was band 4, band 5, band 6, 7, 8, 9, 10, 11. How these numbers are coming? You see that lower end of the frequency band, write that as 3 into 10 to the power n minus 1 in hertz, and this upper end make it as 3 into 10 to the power n. So, 30 kilohertz means 3 into 10 to the power 4, that is why it is a band 4. So, this n is giving you that band. So, this is what 3 into 10 to the power 5, that is why band 5. So, this was the scientific community decided that if someone says band 8, radar band 8, that will imply 30 megahertz to 300 megahertz. But unfortunately, this nomenclature was never became followed in the industry, and still the military bands which does not have any scientific basis, they goes. So, the radar people, they give these names. UHF is UHF, same from communication, but after that they give L. Actually, all these are arbitrary, but everyone in the radar field, they understand the meaning of these bands. So, we should know them, that is why I am introducing them. So, these are the names of the band, and frequency wise UHF means 300 megahertz to 1 gigahertz. You see here that scientific thing is not followed. It should have been 3 gigahertz, but it is up to 1 gigahertz. Then L band, which is a very popular band in satellite industry, it is 1 gigahertz to 2 gigahertz. S band, which is a very popular band in various applications, sometimes satellite applications, sometimes even defense application, it is 2 to 4 gigahertz. Then C band, it is a very good band for satellite people. So, it is 4 gigahertz to 6 gigahertz. Then X band, actually all military radars were earlier in this band. It is from 8 gigahertz, exactly speaking it should have been 8.2 gigahertz, but we can loosely say 8 to 12.4 gigahertz. Then Ku band, you see that K band will come later, but Ku come earlier. So, it is 12.5 gigahertz to 18 gigahertz. Then came K band, 18 gigahertz to 26.5 gigahertz. Then there is a Ka band, Actually, there is a very good, for propagation people, this is an important band. Nowadays, even satellite people are also using this band heavily. And then comes the millimeter band. So, anything greater than 40 gigahertz. Actually, in last 10-20 years, there is another band came which is called terahertz band. Roughly, you can see that millimeter wave is extending up to 300 gigahertz. After that, anything is loosely called terahertz. So, early radars, they, as we have seen in the development, they operated at HF band, high frequency band. So, according to this nomenclature, high frequency 25 megahertz means that will be HF, but why that was used? Because that time high power sources, radar always needs high power sources. So, high power sources were easier to develop at HF band in those days, because communication technology was there to simply modify that and give some high power things. So, that is why, but the drawback of that is, if you are smaller in frequency, there is a problem. Actually, if you have any antenna, the antenna's angular resolution, that means, or I can say that antenna's beam width, you know, any arbitrary antenna. Now, this all these radio waves which are not in the frequency of light, or even actually light also. Now, anything when it radiates, any antenna when it radiates, there is a beam, it is not a straight line thing. But in case of light etc., the beam width is so small that we almost say that it is a straight line thing. Now, in case of these microwave things, the antenna that has a beam width, now beam width means suppose the beam is like this. So, we say that this is the peak direction and from some reference, and then generally we come that okay, compared to this radiation, if it is a power radiation, then 3 dB down locate 2 points. So, then from that reference you get these two, this angle is called the antenna 3 dB beam width. Now, you see in our antenna courses we define all these things in beam width. Now, unfortunately, this antenna's beam width is, we can say, inversely proportional to the antenna's dimension or antenna's aperture in wavelength. So, the fallout of these is that suppose at 25 megahertz, at 25 megahertz, to get a 1 degree beam width, because why I need smaller beam width? Because beam width means in that portion my maximum power is concentrated. So, suppose if I want to detect something, if I can localize the power, then I am making efficient use of the power, but if I spread the beam, then lot of portions are getting illuminated which are not wanted, my information will not come from there. That is why it is always good to have smaller beam width, and later we will see that on this your resolution in the angle etc., angular resolution depends. Okay. So, if you do the calculations, antenna people can do the calculation that to get a 1 degree beam width at 25 megahertz, if I have the best possible antenna, suppose a parabolic dish reflector antenna, I require 105 meter dia antenna, 805 meter dia. You see in our home we see 1 meter dia dishes, 1 meter, 1.3 meter etc. Think of 805 meter dia. So, it is not a practical system at 25 megahertz. But the same thing, suppose I scale up that at 60 gigahertz I require the same beam width, I can show that it will require only 30 centimeter dia. So, you see the advantage that if I go to the gigahertz range, the thing become practicable. So, that is the need of microwave technique. But then at the microwave technique at the high frequency, it is a gigahertz range, there the lumped circuit model does not work. So, I will have to go to the distributed circuit model, and if I go further up, 70 gigahertz is actually a millimeter wave region, there not even the distributed model, there I will have to find the optical techniques etc. required. So, these are the things. Now, let us start first with a so before that I can say that radar, we should remember that radar is a very good sensor. Obviously, when it is detecting, that means it is a sensor. Now, what are the primary functions of radar? First thing is, as the name suggests, that the primary function of this is detection. There is no doubt about it that I will have to detect whether there is an object or not. Now, that does not mean that I am doing any measurement, but radar also, nowadays radars, they not only say that okay, there is something, they also make some measurement. So, what type of measurement a typical radar makes? So, measurement, it measures, first thing is range, that we see that every radar should measure range. Also, it can measure the position of a target. It can also be used to measure velocity, because from mechanics, if I know that if I know the position and if I know this position as a function of time, easily I can find velocity. That is the principles of mechanics. So, velocity can be done. Also, if I know velocity correctly, I can find out also the other accelerations etc., but those are not generally a thing. Up to velocity generally radar measures. Also, you see that to specify a particular object, if I know the range of the object, then actually I am in a coordinate system 3 dimension, I am using only 1 dimension. So, that means there are lot of places where that target may be, if I specify the range, because suppose if I say that some object is there at a distance of 10 kilometer, basically I can say that on a spherical surface anywhere it can reside at a distance of 10 kilometer, that means at a radial distance of 10 kilometer. So, to exactly specify the thing, I need to have 2 more informations. You see, in a global scale, these are sometimes called azimuth and elevation etc. And so, that means 2 more angular informations are necessary. So, radar also measures angular directions. So, the moment I know angular direction, and if I know it as a function of time, I can measure also the angular velocity. All these are vector quantities, 3D quantities. So, these are generally measured. So, sensor, the radar sensor detects, the radar measurement, and nowadays with the advance of radar technology, another job of radar is coming, that is called classification. So, after measurement you also give more information that what is the class of the target. So, here one thing is, can you say what is the target type, what type of target it is? Is it a bird, is it a plane, is it a missile? then what is the shape of the target? What is the size of the target? And finally, this is leading to, can you give me an image of the target? Now, image means a description, maybe in 2 dimension, maybe in 3 dimension, of very small dots or pixels per day. Can you give that? Now, actually the radar is going here, the image it is giving, that image may not be comparable to the optical camera image, but it is going into this direction. So, a radar technique student, he should be aware that the radar sensor, it can be used for all these things, these 3 major things. It can detect, it can be used as a measurement tool, it can be used as a classification tool. Now, let us come to a very basic design of the, or very basic model of the radar, because it is a complete system. That system consists of certain things. Obviously, it is a, you see that this system, there will be radar as a system, we are saying. So, what does that mean? System means it can be called whether it is an active system or a passive system. Now, the meaning means that if I actually, radar works on radio waves. Now, radio waves are always present. You see that everywhere the radio wave is present, even in the outer space also there are radio stars. So, they are creating a background radio noise. So, now from that, so every object is absorbing that and scattering that. So, some radars they detect that. That means, they do not give their own source of power, but from the background, the every target that is radiating some radio waves and it is detecting that, the radar, those are called passive radars. But it is a not very good technology. So, people in radar things, they generally go for active radars, where they themselves pump some power, radio waves, known signal, etc., known power, and then find out what is the echo, and from that they try to do all those sensing functions of detection, measurement, classification. Those are called active radars. Also, radar has a transmitter. So, an active radar has a transmitter, and all radars have, whether passive or active, they have a receiver. Now, if this transmitter and receiver, they are co-located, then it is called a monostatic radar. Monostatic, that means transmitter and receiver co-located in the same place. If not, if they are separated, they are called bistatic radar at different location. Okay. Then what is the medium between the, so I can say that I can see this is a radar. Now, this is a target. Now, in this radar block, there can be, if it is a monostatic radar, there is a transmitter, there is a receiver. If it is not a monostatic radar, then there will be a transmitter block, there separately there will be a receiver block, but all of them will have a target. Now, there is a medium in between. So, this is the intervening medium. Now, what is this medium? Based on that, there may be a, so it may be a in the outer space there will be some type of medium, in the atmosphere there will be some type of medium, in the lower atmosphere and upper atmosphere the medium is different, etc. So, medium also needs to be known. Then when we say transmitter, question will come, what is the power, what is the power, what is the frequency, what is the antenna used, what is the waveform of the radar signal. Similarly, in case of receiver, the question will come, how much small signal it can detect, that means what is the sensitivity of this receiver, what is the noise sensitivity of the receiver, what is the signal processing done in the receiver, etc. So, based on this we will have to change the models, etc. So, the first thing that we will see is what is the basic model or the most simple, because you see we engineers we always try to give a complex problem. A radar is a complex problem, a complete system. Now, unless and until mathematically we use model it, we cannot play with it. So, all engineering studies are basically modeling, mathematical modeling the actual system. So, we will also approach this radar study, this whole course will start with a very simple model which we will be calling radar equation. Though the name is equation, it would have been more appropriate had it been called a radar model or something. So, this is called radar equation or radar range equation, etc. Now, we will see in the next class, but we will start from here, that what is the model. We will take a general case, that this is there is a transmitter, there is a receiver. Now, here deliberately we have shown them separately. If it is a monostatic radar, they will be co-located, these two blocks, and this transmitter is connected to an transmitting antenna. Now, from there is a target here. Now, from here electromagnetic wave will go here, the target will be illuminated by that, then target will take that energy and scatter back the energy. Remember, scattering is different from reflection, that it is not plain reflection, because depending on the body it will scatter how much power, that depends on the body. So, a metal will reflect the whole thing, that means the whole energy it will reflect. A non-metal will reflect some portion of or will scatter some portion of the thing. Now, depending on the shape, depending on the size, depending on the material of this target, how much energy will be scattered, that will depend. Also, in which direction how much power will go, that means angular distribution of the scattered power, that also depend on the target, etc. So, we will say always, that is why scattered energy, that means it is a secondary phenomena. Initially the target is getting some illumination from the transmitter, then it is re-radiating that means it is scattering, and a portion of that will come to the this receiver also will be connected to an antenna. This is an antenna, this is also another antenna. So, the scattered energy, this is the scattered energy that is coming and falling here. The receiver through the antenna is taking that, and then it will do some processing and do those functions, detection, measurement, classification. So, this is our problem. The whole thing in between, this is a medium. Now, this problem we will have to convert to a mathematical model, that is radar equation, that we will see in the next lecture. Thank you.